I'll go ahead and introduce the second speaker right now. The presentation will be Thermoplastic Composites for Infrastructure Applications, be given by Andrew Schanck. He's a research engineer here at UMaine in the ASCC. And his work focuses on composites for transportation infrastructure, and he does a lot of advanced numerical modeling. I'd be remiss if I didn't say that, he's beside me all the way in this kind of stuff, okay? So he's one of the people that I rely on very much to keep me on the straight and narrow and execute a lot of the research that we do here. He got his PhD in civil engineering from UMaine in 2021. He also got his MS and BS from UMaine. He's a licensed PE in the state of Maine, lives with his wife and 3 children in Old Town. So Andrew, I'd like to welcome you up here to give your presentation.
Thank you very much, Bill. Let's get away from my ugly face there. So today I'm going to talk to you about thermoplastic composites for infrastructure applications. So basically what this is going to be is an overview of UMaine's research into thermoplastic composites and especially in their implementation into infrastructure applications. So as by way of just sort of an overview of my presentation, I'm going to tell you pretty much why we care, why we're doing this. Then we're going to talk about the continuous forming machine, which is a machine that manufactures continuous thermoplastic composites that the University of Maine has developed and is currently developing. I'm going to talk to you about thermoplastic rebar. You might see that you each probably still have a specimen of that on your tables, just for some tactile stuff there. I know people like tactile. I'm going to be talking about hybrid advanced additive manufacturing, or HAM, and that's basically taking reinforced thermoplastics and additive manufacturing and combining them so that they can be used in infrastructure applications. Finally, I'm going to talk about future implementation. How do we get this out there on a bridge, on a road, in a culvert? What do we do? So first, thermoplastic composites. Why do we care? Why am I talking about this today? And although I really should start out by saying, what is a thermoplastic composite? So a thermoplastic composite is a composite of a thermoplastic and a reinforcement. No surprise there, but a thermoplastic resin or a thermoplastic matrix that goes into a thermoplastic composite is one that you take a chemical that can be melted below its or above its melt temperature and get it into a viscous state, and then as it cools, you can be reformed into as it cools. This is as opposed to a thermoset resin, which is cross-links due to a chemical. Cross-links due to a chemical reaction, and you can't get it back. You try to heat it up, it'll kind of get rubbery and nasty and kind of burn, but you can never form it into a different shape. In order to recycle it, you need to sort of grind it up and put it into a filler sort of thing. So that's just a basic so you have a basic understanding of what a thermoplastic composite is. So continuing on there, why do we care? So there are some problems that are being faced in our transportation infrastructure. Biggest one, and the reason why a lot of us are here, is durability. So traditional material systems tend to deteriorate. Talking about steel. Steel rusts, we all know that. It's a big problem. So steel, not only steel sections, but steel rebar especially rusts, and that causes spalling, that causes lots of problems with the inflow of water, and that's just not something we allow to deal with. It decreases the lifespan of our infrastructure and just causes lots of problems. Second, there's a sustainability problem. Once we have loss of section, once we have structures that are no longer working the way they need to be repaired or they need to be replaced. That takes a lot of materials. It takes a lot of money. It just takes a lot. And we don't want to have to do that all that much. And also the more traditional materials that we use, it's harder to recycle. Steel, it's pretty recyclable. Concrete and concrete rebar, not as much, and especially not thermoset rebar, which I'll be talking about a little bit later, which would be very, very hard to recycle. Finally, age. We all know, or at least I think we all know, at least I know very well, this part of my shtick, is that a lot of our infrastructure is very old, and that exacerbates the problems above. So there's a lot of problems that we face, and one possible promising solution is thermoplastic composites. First, they're durable. So FRPs, fiber reinforced polymers, like thermoplastic composites, are highly resistant to corrosion, and they improve design life. So there's no steel in a thermoplastic or a thermoset composite. There's no tendency for it to rust. And so that eliminates that problem from the equation and allows the possibility of increasing the design life of our infrastructure to much longer lengths. Second, it can be sustainable. So thermoplastic polymers can be recycled. It takes a little bit to recycle them, but they can be recycled many, many times. And this is as opposed to thermoset polymers, as I mentioned before, that cannot be recycled because they can't be melted into a viscous state and reformed. Lastly, composites tend to be efficient. We don't need, so for instance, with a steel girder, we have a lot of excess material that we don't actually need. So, but with composites, with thermoplastic and thermoset composites, we can put the reinforcement exactly where we need it to meet the stresses and the deflection criteria that we need and not have any reinforcement where we don't need it. That means we can come up with an efficient design with with little wasted material. So now the question becomes, how do we take thermoplastic composites and make them? How do we get them into a form that we can actually make structural shapes or different profiles in an efficient manner? So enter the continuous forming machine, the CFM, which enables our structural thermoplastics. So what is the CFM? What does it do? So the CFM is a thermoplastic composite pultrusion machine. So pultrusion of thermoset plastic or thermoset resins is pretty standard. You take reinforcing plies, or not plies, you can take reinforcement and you pull it through a bath of resin and through a die, and in that die, the resin cures, and at the end you get your profile. So that's well and good for thermosets, but thermoplastics have a problem. Whereas thermoset resins tend to be very liquidy, very non-viscous, sort of like water before they've been cured. Thermoplastics tend to be much more viscous, so like a peanut butter or a honey. And that causes problems because if you try to drag your toes through that peanut butter or honey, they don't consolidate very well. They don't sort of commingle very well, and you don't get a very good part at the end. So this problem has been going on for quite a long time. Quite a few people have been trying to solve this problem. And so what we've done is we have decided we just don't want to deal with the problem at all. So rather than trying to dip our toes through a polymer bath, we just start with tapes. The tapes are already commingled. The tapes are already consolidated into a form where it just comes on a roll, and we can take that entire roll of material through a heated die, and then through a cooled die, come out with the shape that we need on the end. So the benefits of this are that it's fast, it's automated. As I'll mention in a little bit, it's not limited to a single material. We've tried a number of different materials, and it has all come out relatively well. And it's a non-reactive process. So there have been some attempts to use a reactive thermoplastic composite through pultrusion, which has worked. But the problem with that is that those reactive thermoplastic composites, as they're being worked and as they're being set, give off a lot of volatile organic chemicals, VOCs. And that can be dangerous to the operator and dangerous to the environment. So having a non-reactive process is good. So some of the production capabilities, some of the things that we've done, pulled through our pultrusion machine, the CFM, we've done plate and profile stock, so flat plates, channels, curved profiles, the cool little egg carton shape you see over there. That's kind of a fun one. We've also done rod stock and rebar. So we've done smooth rod, we've done rebar. So you have some examples of that in front of you, and I will be talking about that more in a little bit. And in the near future, we're going to be incorporating filament winding to the process, as well as creating hollow sections with a hollow die. So one of the first things that we did once we had the CFM online was to see what types of thermoplastics and combinations of thermoplastics and reinforcements can we use? So we did this with a statistical design of experiments. So some of the candidate materials that we used were E-glass and polycarbonate, E-glass and PETG, E-glass and ILN6, carbon high-density polyethylene, and carbon LM-PAKE. That's a very long word that I'm not going to try to pronounce. So some of the factors that we varied as we made different specimens were the initial heating initial heating temperature, the preforming temperature, the cooling temperature, the line speed. And we did all of those at high-low levels. So that gives a matrix of a number of different specimens that we were going to test in that production capability. And then we measured the response of the resulting specimens. And we tested the longitudinal strength, matrix shear strength, and for the the semi-crystalline matrices, we also tested the crystallinity. So we used all of that data that we collected, all of the trial runs that we did, and all of the specimens that we tested to come up with empirical models that allowed us to predict the quote unquote recipe for a ideal bar that we made through using a particular material. And so those empirical equations or empirical models allowed us to create that sort of ideal ideal bar, and we tested them. And so you can see down there on the table on the bottom, we had very small amounts of model error between the actual results and what the model predicted. And that shows that we can use a variety of tape materials and maximize and predict the response based on input parameters. And we can produce, So now that we've shown that we can produce, what can we do with it? Because we don't want to just make a machine that makes something and then not do anything with it. So that moves us to thermoplastic rebar, which is our first development towards an application. So thermoplastic rebar has a bunch of advantages over top of steel rebar and thermoset rebar. So thermoplastic rebar does not rust or corrode, and that prevents section loss due to spalling. And it can be bent in the field, which thermoset bar cannot. So some of you might have examples of prototype bent bars. That's sort of our practicing bending, showing that we can. I don't have one. I need a prop, but you know what? I'm gonna get one. So this is one of our basic props, our practice attempts at bending. So you can see it's a little bit rough so far, but this is just our sort of refining our bending methods. So this will be improved in the future as we continue to develop this. So some of the additional benefits to FRP rebar, it's lightweight, so it has low density and leads to a high strength to weight ratio. And it's also sustainable. As I mentioned before, it uses a non-reactive process, which combined with a high, and can be combined with the high durability and recyclability. So one of the things that rebar has to do is transfer shear to concrete, or else it's not going to have strain compatibility. It's not going to be useful for really anything. So what we're doing right now is we're testing different methods of shear transfer between the rebar and the concrete to find out what would be the best method moving forward. So the methods that we've been trying are roll forming, sand coating, and filament pole winding. So roll forming is we take the newly minted bar of rebar before it has deformations, reheat it, and pull it through two rolling molds. And this imprints the sort of classic rebar shape into it with the little lugs on this side. And we have a number of different patterns that we're trying with that to see which one works the best. With sand coating, what we do is we heat the outside of the rebar and then dip the entire thing in sand so that that sort of grit stays on the outside of the rebar. And finally, in filament pole winding, we take that newly minted bar, we push it through a pole winder, and that spins really fast and applies tape to the outside to form lugs similar to the roll forming, but rather than having it imprinted, it's put on the outside. So the current status of that with roll forming, a bunch of specimens have been manufactured and testing is in process. We're seeing some positive results, but it's a little bit too early to make any conclusions. We have eliminated sand coating, and that was really just because it didn't work very well. So heating that up caused it to deform too much, and it was just kind of awful. So we abandoned that. And also we've heard from contractors that sand-coated thermoset bar, they really don't like using it. It rips up gloves, it injures people. And so we decided, let's just get rid of that one. Finally, pole winding manufacturing trials are going to be starting soon. We have our pole winder online. It's just finishing commissioning very soon. So finally, the next step after this to bringing this to market is through codification. So acceptance in design standards gets us on track for industry acceptance. Materials used in infrastructure are governed by codes and standards of practice for QC, QA, and thermoplastic rebars are no different. So the goal we have is to amend thermoset rebar standards to accept thermoplastics rather than to write new codes. And this is because they have similar enough behavior and they have some small differences that we would expect, but we just need to address them rather than write an entirely new code. And it is possible that this could be done in the next 3 years if we don't run into any major issues. We'll see. So this is a difficult task. It requires a lot of testing. So here's a list of many, if not all, of the ASTM standards that we will have to meet in order to qualify our thermoplastic rebar to be accepted into the ASHO LRFD code, as well as the ACI code. So we have a long road ahead of us, and we're plunging on towards that goal. Finally, as sort of an additional fun little thing, we want to be able to not only extend the sustainability and the we basically want to, rather than having to ship rebar to the site, we want to ship the manufacturing site to the site. So we are developing the ISO CFM, which is a condensed CFM into a 20-foot ISO container, which is optimized for rebar production, limits power consumption, and has little operator intervention. So the entire idea is to bring the entire manufacturing site to the site so that we can just ship tapes rather than shipping lots of rebar over and over again. And so the status of this is that the design is finished and a shipping container is ready for construction. You will see it tomorrow if you take the tour. I am seeing that I do not have any more time. I would love to talk to you more about hybrid advanced additive manufacturing, but I will unfortunately not have that time. Basically, what it is combining reinforced thermoplastics and additive manufacturing to bring additive manufacturing into the infrastructure space. So that allows us to, so essentially it turns additive manufacturing material into concrete that takes up compression force, where we have a stay in place form of thermoplastic material that takes up tension forces. So we have a stronger, lighter part than we would have normally. We've had some success with that, and that's ongoing through some shear transfer testing, beam strength testing, and numerical modeling. So just as a way of conclusion, none of this would mean anything if we didn't move towards implementation and application. This needs to be put in, or this can be put into infrastructure once we develop it further enough. So some of the possible applications: rebar, that's pretty easy to see. We want to replace steel in bridge decks. So for profiles that are made on the CFM, we want to use it for sheet piling or utility hangers or stay in place formwork. And then for HAM, we can use that to create any shape that we want and then strengthen it using CFRTP or reinforced thermoplastic plates. So I have a little block diagram here, just basically showing what's the combination of things leading to an application. So we have a material system we want to use. We've developed manufacturing methods, combined them, made products that are towards the end goal of an application. So thank you very much.